Hi, today we're going to give you some hints and guidelines for working on the latest and last practical exercise in this semester, practical exercise 6, which is concerned with code generation in our compiler. So there are quite a number of topics related to code generation, and we split this in two parts, and we expect you to work on both parts in this exercise. And some of these parts are smaller, some are a bit more complex, so I think it'll work out well. So first we have to work with global data types like global strings and global variables, functions, function parameters. So these have to go, especially the global strings, variables, and functions into global tables. And then we'll have to work with arithmetic expressions and statements, assignments of results to variables, and of course print and return statements. And in part 2, we'll have to deal with things inside of functions, so local variables, also calls to other functions, and then finally control structures like if, so conditionals, and testing for relations in expressions, while loops, and the continuous statement. So we finally arrived on the right hand side of our compiler structure here. So we have our intermediate representation, and then we're going to build our VSL compiler backend to generate assembler source code here. So we are delegating the task of actually generating machine code and an executable program to the system assembler and linker. That makes it quite a bit easier. So in order to generate assembly code, we need to translate our intermediate representation, which is a tree or tree address code or whatever, into, well, assembler source code for x86 64-bit. And to do this, we primarily have to perform two actions. The first one is selecting instructions, and the second one is allocating registers. So let's take a look at Hello World in assembler. So at the top left, we have our VSL source code example program, which just has a function hello, which prints hello world and returns a value of 0. And on the right hand side here, we see an assembler program on Linux. And this assembler program, as you see, has two sections, a data section and a text section. The data section only contains two strings here. Strings are represented by the pseudo assembler instruction ASCII Z, which means it's a series of ASCII character terminated by a 0 automatically, so you don't have to write that 0 as in C. And in the text section, well, we have a declaration for a global symbol main, which is not declared here because we only have that one function. And then we have our implementation of hello. So usually we prepend our functions with an underscore in order not to have any conflicts with system functions like printf, which don't have underscores. Note that this is convention on Linux. On Mac OS X it works a bit different, and we'll talk about this a bit later. And then finally we have the x86 64 machine instructions implementing the function here. And in order to assemble this to an object file and link it, we can call the assembler separately. So we generate proc.o from our .s assembler source file. So this is our linkable object file. This is not directly executable. And then finally, we call our C compiler with -o to generate the executable program proc from our object file proc.o, and this execution calling the linker via the CC frontend automatically links our C library, so that makes life easier. So when we call CC like this, it's not actually calling the C compiler. Remember, CC is only a front end to all parts of your compiler. It's just executing the linker with a number of convenient shortcuts for us. Now, if you take a look at x86 64 assembler examples for Linux, please take care. Of course, I know there's lots of stuff out on the net, but very many examples I looked at actually use another assembler, which is called NASM, which comes from Windows. And NASM actually uses an incompatible syntax to the binutils style GNU assembler we are using here. So NASM uses the Intel syntax, which especially names registers a bit differently and most importantly reverses the order of parameters. So if you want to use examples found on the net, please remember if it's NASM syntax, reverse the parameters, and some bits of syntax also have to be adapted. So we use a version of binutils, which is a part of the GNU toolchain, so either part of the GCC binutils toolchain, and Clang, so the new compiler toolchain, for example, that's used on macOS 10, also uses an assembler which is source code compatible. And this uses a different syntax, the Unix or AT&T assembler syntax. And, well, there's two standards out there, so we're using the one that's most common on Unix here. So if we have this program here, we can try to assemble it. That actually works out of the box. And when we then try to link it using our CC compiler frontend, actually our linker complains. So our linker complains, as you see, it's complained by the linker because it's the complaining program is used in LD, so our linker. It says proc.o has a problem, and this problem is that there's some strange relocation rx866432s against .data cannot be used when making a PIE object, a position independent executable object, which is a norm on Linux nowadays. Recompile with -fpie. And then our linker refuses to link our program. And the problem is that the two instructions here marked in red on the left hand side, the two move Q instructions, actually try to encode an absolute address here. And this is no longer advisable because absolute addresses make it easy for attackers who try to exploit security holes to actually guess addresses. So usually modern Linux systems actually try to move code and data throughout its virtual address space in order to provide as little predictability as possible for an attacker. And this means addressing strings using an absolute address is no longer allowed. So this moveq instruction would replace these parameters $str0 and $strout with the absolute addresses of our two strings in the data segment. And this no longer works. Our linker complains. We could do something against it by telling our linker not to provide a position independent executable, but we can actually do better. So the first thing we can do that's better is actually we replace our loads of absolute addresses, which we used with moveq before, by these two instructions mentioned in blue here. So now you see the addresses are still str0 and stроut for our strings, but they're relative, and they're relative to register our IP, which is our instruction pointer. So what our assembler does when it encounters this instruction, it actually figures out the distance between the string in the data segment, so the address of the strings stроut and str0, and the location of the instruction that's trying to access them, so it just subtracts one from the other, and then just uses this relative address, which is automatically added to the value of the instruction pointer, with the LEAQ instruction here, and loads this into RSI for str0 and RDI for stроut respectively. So after this LEAQ, we again have absolute addresses, but they have been computed on the fly now while the program is executing by adding the value of the instruction pointer to the offset to the string in our program here, instead of providing direct absolute addresses in our program. Hooray! So when we assemble this and link it, it works, and we get a program that's executable. And when we try to start this program here, well, we get a segmentation fault called up, so our program crashes. So, my goodness, what's happening here? Let's take a closer look. So, if you look at the instructions in blue here, you see that we do something with our stack. And that's a problem on 64-bit x86. And this is that all system functions actually require a given stack alignment. And the stack alignment means that whenever you call a function like printf or putchar, then your stack pointer has to be a multiple of 16. So if this is not given, then actually your program complains and it crashes and you get a segmentation fault. Now the problem is when you enter main, then it's fine. So the operating system takes care of providing a stack pointer that's aligned to a multiple of 16 bytes. But then what you do is call hello. And by executing a call on x86-64, what the CPU does is it pushes the return address, so the address of the instruction after call hello, so that red instruction here, onto the stack. And on x86-64, this return address is 8 bytes long. So our stack was 16 byte aligned before. Now it is 8 bytes lower, so it's no longer evenly divisible by 16, so it's no longer aligned. So what we have to do is we have to subtract 8 from our stack pointer in order to make it aligned again. So we know we had an offset of 8, so we have to add or subtract another 8 because our stack goes downwards in order to be divisible by 16 again and our system not complaining anymore. So that's a bit unfortunate. That's a requirement. This requirement actually also is given on ARM64 processors in case you want to write an ARM backend. Well, this is something you have to take care of because finding bugs like these is really horrible because they're not really obvious. It's not obvious what's going on. Your code looks correct and you just didn't know about this convention. So we see that it's actually rather straightforward to generate assembler source code and then having the system take care of the rest. So what do we need for implementing our program? We need to implement a main function, we need global variables. So global variables need immutable memory, we need arguments, we need expressions, assignments, and we also need print statements, which in turn take expressions again. So our main function, well, is a bit special in this case here, because, you know, main gets a number of parameters from the command line on Unix, but these parameters are not handled like typical function parameters. So you don't get a main function with parameter 1, parameter 2, parameter 3. But main has a special convention here. And this special convention is that main is actually passed 2 values. Or in effect, it's 4 values. But for our cases here, it's 2 values. And the first value is an integer, giving you the number of arguments that were passed on the command line. And this number is always 1 or larger because the first or the zeroth argument actually that's passed is the name of the executable program itself. So since every program needs to have an executable name, this means we always have an argc of 1 or larger. And if argc is 2 or larger, we have at least 1 argument after our program name on the command line. And you can find all the arguments, including the program name itself, as the 0th argument in argv. So that's an argument vector. That's an array of character pointers. And this just gives you a pointer to a null terminated string. So even if you input a number on the command line, it's actually treated as a string. So you have to take care of converting it. And you have to take care of going through this. For all other functions, we have the calling convention from our x86-64 assembler lecture on the instruction set. So we know for all other functions except for main, the first 6 arguments go into registers RDI, RSI, RDX, RCX, R8, and R9 in this order. And if we have any further arguments, they have to be transferred on the stack. And again, our stack will need 16 byte alignments. And we've seen all arguments in VSL are just 64-bit integers, so that makes it a bit easier. And only main is special in this regard. Of course, argc and argv are also just treated like regular parameters. So argc is passed in RDI, argv is passed in RSI. So if we want to build a generic main for VSL functions, we built a bit of this already for you in our skeleton code to make life a bit easier for you. So what we have to do at runtime here is we have to find the argument count, argc. If there are actually arguments, we have to translate them from, for example, text to numbers, because we don't have any text data types except for static strings here. We have to put them in the right places for an ordinary function call, and then we just call the first function defined in our VSL source program. So VSL doesn't actually need an explicit main function here. And then when this function returns, we take its return value and return it to the calling shell. For example, by passing it to the exit system call as a parameter and then return to our shell. And then our program is finished. So we have already provided this generate main function here. This simply generates assembly to point to the symbol. That's the first defined function in the program. And this expects global names to be prefixed with the underline in the generated assembler. And it will fail if the shell provides an argument count that doesn't match the argument count of the starting function in the source program. So that will automatically complain if you try to start your VSL program with the wrong number of parameters. And we have a hard-coded main to prevent the assembler from complaining. And you can replace this by starting off with the symbol T you actually supply. So we also provide a generate string table functions, which already prints a very simple string table that already contains 3 entries in the data segment. So the first one is just a format string for integer output, which has the string of %LD. So this is a format string used for printf in libc to print a long decimal integer number. So essentially an 8-byte integer number, 64-bit. We have another format string str_out, which just is the format string for printing a string, %s. And finally, we have another string, which is our only error string here. We automatically generate from main. If it's the wrong number of arguments, we just, output that it's the wrong number of arguments here. The other contents of the data sections are still missing from the source, so you should generate them here, and you should give them just numbered labels from your string table, like str0, str1, and so on. Now note that we do not generate a read-only data section here as would be expected. We actually make our strings writable. And the reason for this is actually it would work to generate a read-only data section on Linux, but the macOS assembler actually complains. So for macOS, just using data as a section works, and this also works on Linux. This is not ideal, but this is a workaround we can use for now. We also need mutable memory for global variables, just because, of course, these global variables can have their value changed. So again, we need to emit a data section here, or we can just add to the data section whatever you like. The assembler just has no problem with having separate data sections, and it unites them into one. And then we just generate labels for each of the global variables, such as x for the variable x, and usually for labels we add a colon to it, so our assembler can figure out it's a label. And remember, labels always start in the leftmost column of a line, so they're left aligned. And then usually we place a 64-bit 0 value at that address, so the program can change this at runtime, and our variables are guaranteed to be initialized. So we could say x colon means we want to declare a variable x, which is a global variable, and then we say dot is 0, so it contains zeros, and it contains 8 bytes of zeros, so this would be a 0 initialized 64-bit value. And then whenever we access a global variable x, reading or writing, we just translate it into an access to our variable, to our label x. And remember, these accesses also have to be PC relative, so instruction pointer relative. Using global addresses is no longer supported here. Well, arguments, we've already seen that the first 6 arguments to a function reside in registers, and we've seen the registers here. And for convenience, the call convention order is also placed in a static string array record of 6, which contains strings with register names in order, so you can use them to actually generate code that accesses parameters. So you can access record of 0 to get the zeros parameter, record of 1 to access the first, and so on and so forth. So for function calls, these registers obviously will have changing values here. So what you should do is you should provide copies of the arguments, and you can place them on the stack as you would do for local variables. And that's actually the first thing a function does. So essentially what you do is you copy out the RDI, RSI, and so on values into a local variable so you can modify them. And these can then have an address of base pointer on our stack plus 8 times the index of the argument, so they don't interfere with local variables. Stack alignment, we've already said, we need a 16-byte stack alignment. Accessing arguments takes place relative to our base pointer from the bottom up, and every argument at local variable consumes 8 bytes. So if we push an odd number of variables, we would create a stack misalignment. So if required, please pad it with 8 additional bytes, so a dummy variable or whatever, which then prevents crashing of the generated system call instructions, so like a call to printf. What else do we have? Expressions. So for expressions, we would treat our process just as a stack machine when generating code, and then the accumulator register RAX would contain values and results. So numbers would just translate in a mu of q of the constant into the RAX registers, whereas variables would translate to copying the variable contents into the RAX register using an instruction, as we've seen by loading an address and then dereferencing it IP relative. Operations that can then be translated recursively by going through your tree. So you first generate a sub-expression 1, put the result in the RAX, push the result. Step 1 then will be repeated for sub-expression 2. Then we can combine the result when you walk down the left and right part of your expression tree with the top of stack element. So you generate the additional instruction to combine the two sub-results of your sub-expressions. Then you can remove the temporary result of sub-expression 1 from the stack, and the result is then in RAX, and the stack is restored. Take care of multiply and divide instructions because they have special constraints for registers they can put results into. Assignments are then very easy because you still have the result on the stack when you evaluated your right-hand side expressions. So assignments are implemented by just generating code for the right-hand side expression and then moving this result, which is an RAX, to whatever location the destination on the left-hand side has. Then we have printing. So parameters for print instructions are lists containing strings, numbers, identifiers, or expressions. So you can actually break this down to generate code to print the first element, and then for the second, and so on and so forth. And finally, print always prints a new line character. So the last part of your print implementation should be to generate code to print a new line character here. And what print does is it simply concatenates its parameters, so it prints them one after the other. So what you can do is actually you can generate separate printf calls for each of your parameters of printf, and well, these are automatically printed one after the other. So you can iterate over the list of print items. So you can set up and call printf with parameter string out as format string and the string when you encounter a string as a parameter. When you have a number, you would call printf with int out, our second special format string we've provided, and then the number as second parameter. For identifier, we would also use int out, and then we would have to evaluate the expression, so the contents of the identified address for the variable containing the identifier. And for expressions, we would generate the expression and then call printf with parameters int out, and the second parameter would have to be copied from the contents of the result of the evaluation, so of RAX. Well, there is more to do. Compilers, especially backends, are quite a bit of work, unfortunately, so there's a bit of more fun to do. We still need to generate code for everything that's inside of a function, like local variables, function calls, if, then else, while loops, and continue instructions. So local variables are not accessed in the same way as global variables, because they're not in the data segment, but they're just located on the runtime stack relative to our stack or base pointer here. And that's why we insisted on having this sequence number and really being precise on having the sequence number. So the sequence number for local variables can actually be used to determine and find their offset from the base pointer. So we just multiply the sequence number by 8 and we have an offset for our variable here. And so when you begin generating code for a function, you would create space for local variables on the stack. So remember the 16-byte stack alignment here again. So in doubt, just do an 8-bit padding if you know you have an odd number of variables on local variables on your stack. And then as you were generating the symbol table, you provided a count for local variables, and you can use this sequence number now as an index. And otherwise, you can just use local variables in the same manner as global variables, just using the offset from RBP now instead of an offset from RIP as for global variables. Function calls are part of expressions, so generating function calls requires you to follow the x86-64 calling conventions. As we've seen, putting the first up to 6 arguments into the designated registers, we've mentioned several times already. And if you really have functions with more than 6 arguments, you have to push them on the stack. Then you have to call the function, and finally, when this function returns, you have to restore the stack and return the result value in the RAX register. You could, of course, define your own calling convention, but this would just be extra effort. And if you ever want to interface with other C code, this would make the interfacing much more difficult. So I would advise against this actually. Conditions. Well, relations are generated in the same manner as arithmetic expressions. So again, you recursively generate code to evaluate the left expression, putting the result in argx, then put that on the stack. Then you do the same for the right-hand side expression. So if you have if a is less than b, then you would generate code to load a, put it on the stack, and then you would generate code to load b, put that on the stack, and then get the results from the stack, do the comparison, and then, depending on the result of the comparison, do a conditional branch, a conditional jump, depending on the condition that was just part of the condition in your if or while expression here. So if you want to implement jumping, so if a equals b, then a else b, can be turned into this pseudocode. So first you have to evaluate the left and right hand side of your comparison here, of your relation. Then you have to compare them, and if they're not equal, then you execute the else part, so you jump over the then part. Then you just generate code for the then part A, and jump over the else part to end if. Otherwise, you just execute the else part, generate code for the else part here, and then you just fall through to end if. And the next instruction after our if construct here then comes after generating the final label end if. Now the problem is, if you have several if conditions here, you might end up with several labels being named else and end if, and that will trip up your assembler. It will complain about doubly defined symbols because it doesn't know where to jump to. So this actually would either need a numbering scheme, since you can, for example, also nest conditional statements. We would need a stack to push and pop the counter values from the numbering scheme, which then will track our nesting here. So this is a bit more complex than shown in the simple example. So it's making it easier when you generate labels like else1, else2, and end if 1, end if 2, and so on. There's also ways to have local generate labels like 1f, 1b in most assemblers to take the first label forward or backward. That's called 1. You could also try to use this. We haven't experimented with this, but this should actually also work. Loops are treated like conditionals, so we have a condition inside of our brackets for a while loop, and then we have an expression. So essentially we generate a label for our while loop here, and the first action we do is we evaluate the condition, and if this condition is no longer true, we jump to the end of the loop, so to our loop label end while. Otherwise we just generate code for the expression and jump to the beginning of the loop. And remember that you have to re-evaluate the condition every time through the loop, so we need to generate this while loop label before we evaluate this condition here. And then we would treat loops in the same way as ifs for nesting, so implement a numbering scheme if you have nested while loops and use a separate stack for these loops, and that should work. And then this should also work to generate nested while and if conditions in one way or the other round. Continuous statements just are used to skip back to the beginning of the while loop they're appearing in. So they skip directly to the condition evaluation, so to your while loop label. So if you have a shared counting scheme for whiles and ifs, then the enclosing construct could be an if. That would be problematic, because then continue would just go back to the if statement instead of the while statement it belongs to. So that's the good reason to use separate stacks for if and while for counting those. So you always have the index of the enclosing while loop when you want to implement continue here. So finally, of course, all this was valid for Linux. Now, of course, many of you have also Mac OS systems. So there's a bit of a difference on Mac OS. And the major difference actually here is, because we adapted the Linux code to also work on Mac OS, is the naming of labels. And the problem is the calling of system calls. So for Linux, system calls are not prefixed by an underline. So you enter, like on the left-hand side, call printf or call putchar, and the linker then finds the symbols in libc. And that works by then prepending all your local function names with an underline, so you don't have any conflicts here. So your main symbol has to be just main, because the linker is looking for that name here, so no underline prepended here. Also, on macOS 10 it works the other way around. So you have to prepend the name of libc functions with an underline and also the name of main. Another problem is that you can actually have a clash here. So if you have a function in your VSL code called main, which is perfectly valid, this would be a clash with our generated main function here. So we could do a number of things here. We could, for example, prepend 2 underlines to our local functions here in order to ensure that we don't have any conflicts. This happened to me, so essentially that would be a workaround. And we've tested these macOS stuff against macOS 11.2 Big Sur and 10.14 Mojave, so that's the both versions I have here. So the other differences I already mentioned. So we use data as a section for strings instead of the usual RO data, since the macOS assembler isn't happy about RO data. I think there's a workaround. I just would have to look for it, but that's the way it works. And the prepending of the underscores would be another thing. Linking might be a bit more effort, so we assemble it as before. And since you could also be on an ARM Mac when assembling this, we actually pass this -arc x86 underline 64 explicitly to tell our assembler. So the assembler can generate code for ARM and for x86. We tell our assembler to generate x86 code here, and then we call our linker explicitly. And to find our system library, we pass -l system instead of -lc for the C library, and then we have to tell our linker where the libraries are located. So that's a parameter -syslibroot, and then we execute a command xcrun -sdk macOS 10 show sdk path. So that essentially is dynamically generating the correct path on your system to print the location of your libraries. Now this requires that you have the Xcode command line tools installed. So either you can have the complete Xcode system installed here, or you can separately install the command line tools. Just Google how to do it if you haven't done this, but you should have done this already, because otherwise you wouldn't have been able to compile anything in the previous exercises. So if this causes problems, just let us know. But of course, what's with my shiny new M1 ARM Mac? We're just generating x86 64 code. So as some of you know, Apple has switched some of their computers to ARM CPUs, 64-bit ARM CPUs, not all systems right now. So if you have one of these shiny new Macs, luckily Apple provided a method to actually run ancient x86 64-bit macOS programs. And it simply works. So this static translation is called Rosetta 2, which is a tool that actually takes an x86 executable, translates this to ARM instructions. So I've given an example of a bit of a translation of our example code on the left-hand side here, and then runs the translated code. And for everything that cannot be translated statically, it has a just-in-time compiler to do this. So by giving this -arc parameter we've shown on the previous slide to our assembler and to our linker, you can actually compile and link x86 64 programs as you would do on an Intel Mac, and just run them, and you shouldn't notice any significant difference. Of course, if you like, you could also try writing an ARM 64 backend, and if you do this, we would be very interested in your experience and your results. So I haven't started working on that actually. So that's all the guidelines we have for this exercise. It's a bit of work, but if you have all of this running, actually, you have a complete working compiler for your simple VSL language that actually generates working code that you can execute. So I think that's a nice result to have at the end of the course. I hope you found this interesting. So thanks for listening. Thanks for participating in our practical exercises. And yeah, have fun. All right. Thanks a lot, and bye.